Now that we have an understanding of Earth's atmosphere from Chapter 17, we can move on and discuss Chapter 18, the winds of the world, global and local wind systems. This lecture will be divided into 3 parts. First, discussing why wind blows. Secondly, discussing tropical wind systems. And thirdly, discussing mid-latitude wind systems and local wind systems. So why do winds blow? We defined wind in Chapter 17 as the horizontal movement of air from one place to another. 3 forces determine the direction and speed of wind. These are the pressure gradient force, the frictional force, and the Coriolis effect. On the right, you see a satellite image of atmospheric water vapor, which helps us identify air currents and eddies, or the direction that wind is blowing. The pressure gradient force is the rate at which pressure changes with distance. Wind results as air moves from a high pressure area to a low pressure area. So in the figure below, we see that on the left, we've got molecules are closely spaced or densely packed together in a high pressure zone. As those molecules try to escape to a less densely packed area on the right, or an area of low pressure, that movement of molecules is wind. So this wind is pushing the sailboat from left to right. A pressure gradient can be represented on a map of constant elevation by plotting contour lines or isobars along which all points are of equal pressure. So in the top 2 figures of a map of Florida and a picture of some palm trees, we have the different isobars or curved lines representing different pressures are spaced closely together or densely packed. Okay, and so when they are spaced closely together, we have strong winds. And in this case, the area of low pressure is in the southeast, and the area of high pressure is in the northwest. In the bottom 2 diagrams, we have isobars that are widely spaced, which indicates weaker winds as you move from the lower pressure area to the higher pressure area. So in this case, we would see sunny weather, very little wind in our photo of the beach and palm trees. Friction occurs when faster moving particles collide with slower moving molecules or particles, or when a volume of air shears against the Earth's surface. Friction always acts in the opposite direction of the air's motion that results in the slowing of the air. The air adjacent to Earth's surface, in which friction significantly affects air movement, is known as the boundary layer of air. Various factors affect the height of the boundary layer, including terrain and temperature. So here are some examples of the boundary layer on above Earth's surface. So the dashed line in the top figure shows the different changing elevations of a boundary layer as a result of topographical differences, changes in temperature from cities or from forests. The 2 pictures below show representations of the boundary layer in different environments. Also would be in a city, and on the right would be in a more natural area. The third factor that affects wind speed and direction is the Coriolis force. The Coriolis force causes objects to veer to the right in the northern hemisphere and veer to the left in the southern hemisphere. This affects direction but not speed, and it is strongest for objects moving fast. At the equator, it has a net value of 0 or no effect. The geostrophic balance occurs when the gradient force and Coriolis force are equal and opposite, and the frictional force is insignificant. In this case, the Coriolis force turns the air's path to the right until it flows parallel to the isobars, or the constant pressure surface. So in the picture on the right, we've got an isobaric surface that is of constant pressure where the area is flat, and where it is curved, that's where we're changing pressure. So we're going from high to low isobars. And then we have the Coriolis force acting to the right and the pressure gradient force acting to the left. These together produce the geostrophic wind that is perpendicular to both. The geostrophic wind blows roughly parallel to isobars at 10 kilometers above sea level, which is the elevation of the jet stream. Winds blow faster where the isobars are closer together, or where the pressure gradient is greater. When temperature is uniform across a region, the isobars are horizontal rather than vertical. And when heating or cooling occurs, these isobars get bent, resulting in a pressure gradient where the air now flows. In this case, low pressures form with warm rising air in the top figure, and high pressures form with cold sinking air on the bottom figure. So when you watch the Weather Channel, if you notice meteorologists talking about a high pressure system, you may experience cool and sunny days with little wind, whereas a low pressure system, you have warm air that is rising, producing wind, and these may be rainy or stormy days. Now begins part 2 of the lecture, where we'll discuss tropical wind systems. This discussion begins with the introduction of Hadley cells, which are global convective cells that cause air to rise at the top of the troposphere, move towards the poles, cool, and sink back towards the surface of the equator. So the Hadley cells are shown in the figure below. Coriolis effect causes these convective cells to deflect east at the top of the troposphere and to flow westward near Earth's surface, creating trade winds and determining the locations of deserts, grasslands, and forests. How does this happen exactly? Well, when trade winds from the northern and southern hemispheres converge near the equator, they enter into something called the intertropical convergence zone. Air in this zone has nowhere to go but up, so it forms the rising part of the Hadley cell, which produces heavy rainfall and thunderstorms in the ITCZ area. These regions are known to be where tropical rainforest exists on Earth, and this is the reason for the production of heavy rains in tropical areas. A notable omission from the previous slide is that when the rain falls in the tropical areas where trade winds converge, as that air rises and dumps all of its precipitation as it goes towards the troposphere, it goes northward and southward and cools. And as that air descends down towards Earth's surface again at closer, at not exactly equatorial, but tropical to mid-latitudes, This air is so dry that there is no moisture in it, and it results in deserts in the areas that surround the tropical rainforests. Now, on to the subtropical jet stream. This is a very fast, greater than 160 kilometers per hour, high altitude, eastward moving river of air at the top of the troposphere. It encircles the globe and can affect weather in the mid-latitudes and tropics. Two jet streams exist in each hemisphere, the subtropical jet stream and the polar front jet stream. The Walker circulation extends vertically between the Earth's surface and the tropopause and horizontally from South America's western coast to Australia and Indonesia. This east-west flowing convection results in colder water off the west coast of South America and warmer waters around Australia and Indonesia. During a La Nina event, the Walker circulation strengthens, moving warm surface waters from the west coast of South America towards the coasts of Oceania, producing heavy rains in the oceanic islands. This is shown in the figures below. The oscillation between La Nina and El Nino conditions is referred to as the El Nino Southern Oscillation, or ENSO. During an El Nino event, the Walker circulation weakens and the surface waters flow eastward in a reverse manner. In this case, the warmer water flows towards the coast of South America and produces heavy rains in this area and drier conditions in Oceania. ENSO circulations have global weather effects as seen below. So in this picture, we see the effects of the El Nino event, where we get dry and cool weather in western South America and warm and wet conditions in Oceania in the wintertime. During La Nina, we get wet and warm conditions off the coast of South America and relatively dry conditions in Oceania and Southeast Asia in the Northern Hemisphere winter. Monsoons are seasonally changing air circulations accompanied by rainy and dry seasons. During the summer, low pressure develops over warmer land, drawing in moist air from over the ocean, resulting in heavy rainfall over the land. During winter, high pressures develop over cooler land, blowing dry air out over the ocean, resulting in dry periods on land and wetter periods in the ocean. The Southern Asian monsoon is the world's largest monsoon, and in this case, the Himalaya mountains trap moisture over the subcontinent of India. This brings heavy flooding, and when rains fail, this results in extreme drought conditions. Mid-latitudes between 30 and 60 degrees experience much more frequent weather changes than equatorial regions. These result from the interaction of cold polar air flowing towards the equator and warmer air flowing towards the poles. The boundary between warm and cold air is known as a polar front, shown in the figure below. So we see warm air moving above cold air in their boundary at the polar front, and that warmer air kind of gets squeezed between the colder air below it and the tropopause above it, and this is what produces the jet stream, which is an extremely fast movement of that warm air. The polar front jet stream is a stream of air over polar fronts which flows west to east in a wavy pattern that tends to shift north in the summer and south in the winter. Finally, we'll discuss local wind systems, which are influenced by land and sea boundaries that generate several different types of local winds. Water has a high heat capacity, which is known as the ability to store heat, and the difference between the heat capacity of water and land produces some unique local weather patterns. This is because wind can be generated as heat is absorbed or released from different locations. Sea breezes are known to occur in the peninsula of Florida most regularly during the summer. And these form as heating of air over land draws in cool air from over the ocean during the daytime, which triggers thunderstorms. Because the land cools faster than water, a land breeze can also occur as cooler nighttime air blows out over the ocean. Lake effect storms also occur as a result of the difference in heat capacity of water and land. The high heat capacity of water means it remains liquid even in the early winter as temperatures are becoming consistently lower. As colder air flows over warmer lake waters, this can generate lake effect storms, producing heavy snowfall. So these two pictures on the left is a satellite image of the Great Lakes region, where snow is covering nearly every piece of land, and the Great Lakes are snow-free. And the picture on the right is of an individual plowing their walkway in front of their house. Mountain and valley winds occur as a result of heat release from insolation during the daytime. So in mountainous regions, heating or insolation during the day causes warm air to flow upward, whereas nighttime cooling results in air to flow downward. Downslope mountain winds occur when you've got high pressure on one side of a mountain range and low pressure on the other. This results in the air rushing down the mountain from the high pressure to the lower pressure zone, and can create downslope windstorms known as Chinooks in the Rocky Mountains, the Santa Ana winds in California, or the Fen winds in the Alps. Finally, we have katabatic winds. These develop when a dome of cold, denser air forms above an ice sheet and then flows into lower elevations. These winds can reach speeds of 160 kilometers an hour and really only occur in the areas where we have continental glaciations in Antarctica and Greenland.